Hey everybody, this is Mr. Chernitsky, and this is Geometry Unit 3, Lesson 3. Um, let's take a look at this jump start. We have this kind of star pattern here, and the directions are, can you find all the missing angles? Well, one thing that we can certainly do is any of the vertical angles. So we got 110 degrees here, so this means that that also has to be 110 degrees on the other side. Same here, this has to be 105. Across from the 80, that has to be 80 degrees. Across from that 60, that has to be 6 degrees. So that's one thing that we could do for any of our vertical angles. Something else that we could do, we could look at our linear pairs. So next to this 60, we have to make 180 degrees, so that's got to be 120 there. And then also across next to that 60, 120 there. Next to this 110, we have to have a 70 degrees. Next to this 110, we have to have 70 degrees. Next to the 105, that'd be 75 degrees. That'd be 75 degrees. Next to the 80, well, we have to have 100 degrees there. See? And that gives us a lot of pieces that we can work with here, okay? But what about within this triangles? Okay, is there some tools that we can use to figure out some of these missing angles within the triangle? So you may have heard that in a triangle, the sum of angles inside is 180 degrees. Okay, just a rule you may have been told. That's something you may just understand by authority. Well, today we're going to try and get a better understanding of that. Okay. So we've been using this tessellation diagram to prove some angles. We're going to look and see can we use it again for some more angle relationships. Okay, so experiment 1. So says sketch a triangle and measure all 3 angles inside. So we could sketch any triangle here. We want to use a straight edge. And we could measure using a protractor all 3 angles. So we'd measure this angle, this angle, and this angle, and see what those measurements are. So that's one thing that we could do. I'm going to use some technology instead. We'll use GeoGebra. So here is our triangle. So we have angle A, it's 43.6 degrees. Okay, and angle B is 48.51, and angle C is 87.89. And if we add those 3 up, we can see we get 180 degrees. And that's pretty neat. Okay, we could even try different triangles. Maybe if I move things around, things will be different. Maybe make it like really obtuse. Well, no, that didn't work, or that still works. Yeah, basically any triangle I make, it's always going to be adding 180 degrees. So by experimentation, we're kind of verifying that this rule is working, but we haven't quite proven it yet. So the angles add to 180 degrees. Okay, so do we prove that those are always going to work? Well, no. The answer is we cannot test every triangle. There's an infinite number of triangles, so all we can do is just kind of verify. So we need something better. And we're going to try this 2 different ways. So we're going to try it graphically, and we're going to try it using a formal algebraic proof. So using our tessellation and our rotations So we can see we're going to do 180-degree rotation. And see, this blue angle is going to come down here. So, and then another 180-degree rotation. And that green angle is going to come around and land here. And we know this is going to work because we know that after 180-degree rotation, parallelism is preserved. So these two lines are going to be parallel. And we know they're going to come around and line up again and be parallel based on this 180 degrees here. And this distance is going to be the same. So through transformations, we're going to see that these three angles are going to line up along this shape. And we haven't defined what those angles are. We just know that it's going to always create that trapezoid shape. So by doing two 180-degree rotations, the triangle forms a trapezoid with its three interior angles forming a line, which is 180 degrees. Okay. All right, so that is our graphical proof. Let's see if we can do an algebraic proof. So here's our triangle, and we have angles 1, 2, and 3 here. And all I'm going to do is I'm going to draw an auxiliary line that is parallel to this baseline here, to the BC. And when I do that, we get a couple of extra angles, which I'm going to call 4 and 5. So we'll set up our two-column proof here. Okay, so one thing that I do see here is that 4, 3, and 5 make 180 degrees. So that is going to be my first statement. So angle 4 plus angle 3 plus angle 5 equal 180 degrees. And that is not a linear pair, but linear angles, let's call them. Okay, so it's three angles that are making a line. Okay. Based on our parallel lines and our other side lengths, so I take that side length of AC, I have some alternate interior angles. So for example, 1 and 4 are alternate interior angles. So my second statement is going to be angle 1 is congruent to angle 4 by alternate interior angles. We know that the alternate interior angles are congruent. We proved that in our last lesson. Over on the other side, with this blue line at AB, we have some more alternate interior angles. We have 2 and 5 are alternate interior angles. So angle 2 is congruent to angle 5. Okay, so now I have those alternate tier angles, we have those as congruent. I'm going to make some substitutions here. So I'm going to substitute 1 into 4, and I'm going to substitute 2 into 5. Basically replacing them since they are congruent. So when we do that, we're going to have angle 1 plus angle 3 plus angle 2 equals 180. So I'm just doing a substitution. And now, algebraically, I have shown that angle 1 plus angle 2 plus angle 3 equals 180 degrees. So that is our algebraic proof that the sum of interior angles adds up to 180 degrees. Okay. The next proof we're going to look at is the exterior angles of a triangle. Okay. So if we extend out one of our sides, we get this angle on the outside of our triangle. We call that an exterior angle. Okay. And our goal is to figure out, well, what is this relationship? Okay. What is 4 equal to? Okay. And if we look at this exterior angle, so we know it's got to be the supplement to whatever this angle is here, but also it looks like it's, if you take these other 2 angles, it will add up, those 2 angles will add up and equal that exterior angle. And so you could measure this with a protractor and see if you measured angle 1 and angle 2, that should add up to be angle 4. Well, let's try this on a graphical proof here, okay? So if we look at, here's our original triangle. And the external angle, if we extend out to that side here, that is going to be the blue and the green together. Well, that just kind of shows right there. The blue and the green together form that exterior angle. So that's kind of our graphical proof. So using our tessellation. So the exterior angle is formed by the two non-adjacent interior angles. All right. That's the kind of visual proof here, the graphical proof. Let's take a look at a more formal algebraic proof. Okay, got our statements and our reasons. So something that we do know already is that 3 and 4 have to make 180 degrees. So we'll start there. So angle 3 plus angle 4 equals 180. That is a linear pair. Okay, has to make 180 degrees. Something else that makes 180 degrees that we just proved, angles 1 plus 2, angle 2 plus angle 3 equals 180 degrees. That is our sum of interior angles theorem that we just proved. Okay. All right, I have two statements that equal 180 degrees. So let's set those two statements equal to each other. We'll do a substitution. So angle 3 plus angle 4 equals angle 1 plus angle 2 plus angle 3. Just a substitution. Okay, and then I look at both sides of this equation and I can see that I have an angle 3 there on both sides that I'm going to subtract off. And what I have left over is angle 4 is equal to angle 1 plus angle 2. So just doing a subtraction. And that is ultimately what we were trying to prove. So the sum of interior angles add to 180. And the exterior angles of a triangle equal the sum of the non-adjacent interior angles. Okay.
Will Dubner please call it?
Okay, our retrieval. So looking at our diagram here, we're just verifying where are the statements coming from. So AB is congruent to BD, which is congruent to DE, which is congruent to AE. This is all done based on the construction. So all the construction circles are the same. This is how we form that rhombus shape. Okay? So those are all equal. Then how do we know that triangle AEB is congruent to triangle, or sorry, BAE is congruent to triangle BDE? Well, we already matched two of the pair sides. And then in the middle, that is a shared side. Okay, so those triangles are going to be congruent. Congruent by side, side, side. And if those triangles are congruent, we can go back and say that any of the angles are congruent. So angle EBD is congruent to EBA. So these two angles will have to be congruent because the triangles are congruent. So because the triangles are congruent. Okay. Lastly, we're going to take a look at a couple of absolute value functions. We're going to graph them. So we'll just go ahead and put axes here. And the thing to remember that if you graph the function f of x equals the absolute value of x, that is a shape that looks like a V centered at 0, 0. Okay, and so these extra little things outside and around are variable. Those are just transforming it a little bit. So this one is going to move the whole function up 1 unit, And this -3 is actually, it's always going to be the reverse of what that sign is. So that's going to be going to the right 3. So our vertex is going to be right 3 and up 1. And then I'll graph like so. Same thing with GVix. We'll plot our axes. And it's -3 tells us it's down 3. And this is going to be left 5. So if we go left 5 and down 3, there's our vertex. And our absolute value plot looks like that. And that is the end of this lesson.